my great pleasure to introduce Herve Moulin. Herve is a professor of economics at Rice University. I'd like to talk about stereo vision, which is, I think, a super exciting field. It has a really proud and fascinating body of literature in economics, and also has seen some attention from computer scientists in the last decade. For example, for things like cost sharing or pay cutting. There are a lot of computational challenges as well that arise in these contexts. And we're also seeing in recent years that some of these techniques in computer vision can be applied in computer science to things like cloud computing. So there's a very, very exciting interaction between economics and computer science around computer vision. And I'm looking forward to this talk.
Thank you, Ariel. So I'm going to be presenting, trying to survey the results of the mostly economic literature on fair division. I mean, what are the few ideas that economists have invented, I believe, and brought to this discussion of fairness, which of course is very ancient. And I'm going to try here and there to make some references to points, to directions where indeed, as Ariel mentions, some more interesting algorithmic or computational questions arise. But I'm not a specialist of those techniques, so some of my suggestions may sound a little bit naive. I mean, we'll see. Okay, so first of all, I must warn you that, especially for those of you who never had particular training in topics like social choice or mechanism design viewed from a normative angle, I mean, you will probably encounter in my lecture number of new concepts, and it's sometimes a little hard to swallow, so don't hesitate to stop me and interrupt and say, explain a bit the concept, because none of this concept is very complicated. I mean, mathematically they are always very simple to describe, but it's the meaning of it which has to be convincing. Okay, so it's always good, I think, when you start talking about fair division to start with the famous Aristotle quote about what's fairness. Equal should be treated equally, and unequals unequally according to relevant similarities and differences. So the first one, equal treated equally, that's what we call horizontal equity. So if agents come to a fair division problem with identical in every respect that matter, then we should treat them equally. But then the hard part is, okay, what are the relevant similarities and differences? That's where, of course, there is always the issue, the big modeling question. And then there is also the very important issue of how do we deal with differences? I mean, it's clear that when you are trying to divide stuff and you have some knowledge of the difference in individual characteristics of your agents, one big issue is whether you want to take into account those differences to actually hold agents responsible for these differences and therefore reward them or penalize them for having more or less of the good or bad characteristic, which could be amount of effort, amount of input, certain qualities. Or on the other hand, you could think of certain types of differences in characteristics as a matter of luck, a matter of random luck for which the agent cannot be held responsible, and then those differences call for compensation, but no penalty or no reward for agents who have, because they are not responsible for creating them. So it's enough to illustrate the point. I mean, just think about the difference between expensive taste versus handicaps. I mean, you are distributing a resource, a useful resource, like food or certain type of medicine, and then you have, let's say that you are dispensing food, and then you have some people who may have some handicaps which make them needing to eat twice as much food in order to get the same calorie intake or calorie or whatever actual output you are looking after. Or you may have some people who are simply greedy or have expensive taste and they want to eat more because it's it's not a biological question, but it's something that in your model you regard as their own responsibility. So depending on this responsibility variable, of course the answers will be very different. So it is not the object of this class to this lecture to try to think more broadly and more deeply about this divide. I mean, what I'm going to do is when I present a model, I will always specify, well, in this model, this particular type of variables, we will think of agents as responsible for those, whereas those others, they are not responsible for. And of course, philosophers and many other social scientists do go much deeper in those issues and discuss some philosophical foundations by which we can enlighten these differences, but that's not what we are about here. We are about here the models that try to make those, once we have those distinctions, how can we make them operational into some actual fair division methods? Okay, all right. So a second concern, which will be throughout the talk, but this one you have encountered already, it's the issue of information and whether the information about the characteristics of the agents is public or private. I mean, that's basically the central theme of mechanism design, and we may have two types of model to just take the two extremes. Of course, you have also intermediate models, but you may have a model in which all the information about all the relevant information about the division issue is public, which gives full flexibility to the planner, to the system manager, to whomever is in charge of implementing the division rule. Or you may have, on the other hand, a model in which private information information about private characteristics, about personal characteristics is private, and therefore we need to give incentives to the agent to reveal those characteristics. It's the problem of preference revelation that we have already discussed in this school in a couple of instances. So that too will, of course, make a big difference. Generally speaking, I mean, when I say consequence, it may be a little bit too strong, but generally speaking, what it means is that when we are talking of model in which we are dealing with cardinal measures of utilities, it's much more difficult to think of them as private information because they're going to induce much more incentives for much more opportunities to manipulate, whereas and therefore when you have context with private information on the characteristics, I mean, it will be typically easier to ask agents to simply reveal preferences because those things tend to lead to less manipulation. I mean, we will see in the results how that goes. Okay, and then finally, I mean, the third point of importance, which of course you are also already familiar with, it's the one thing that you cannot go without if you claim to be an economist. You cannot be an economist who is not concerned by efficiency and Pareto optimality, right? I mean, it's almost, I think of it almost as the definition of an economist. So we'll be trying to put these things together, and the incentive issue of revealing characteristics when they are private information, the efficiency issue, and then, of course, specifically here, the fairness notion, which up to now I've left very, very vague, right? And now I'm going to tell you briefly what I will do today and tomorrow. Well, I will just mention. First of all, I will try, but this really very briefly, to survey a well-developed and I would say rather stable theory where I don't think that there are too many opportunities for algorithmic development, although, of course, I'm surely wrong. But it's the theory, what I call welfarism, which is the theory of collective utility functions. And why we'll need that, I think, will be apparent when we develop the other models, because here there are some basic concepts which I think needs to be reviewed because I do believe that several of you are not too familiar with that, and it's important. Okay, so it's the theory of collective utilities, right? Or some people call that social welfare and so forth. But especially in algorithmic literature, it's often the case that those notions are taken rather light and rather without too much justification. So I just want to bring back some simple foundations there, which are useful everywhere. And it's a case, if you want, in which there is no incentive issues, because it's a division problem in which the system manager has complete control of the feasible outcomes. He can choose whatever feasible outcomes. And agents, based on these outcomes, experience a certain level of utility, of welfare, which is cardinally measured, which is public information, and for which the agents are not responsible. So there is no notion of reward. There is just the notion of, here I take the example of the parent, who has to make, parents who have to make decisions which will affect the welfare of their children. They are completely aware, that's an exaggeration, of course, of the consequence of their action on the welfare of their kids. And the kids are totally out of the picture, if you want. They are just machines to produce utility, in a sense, right? And we just know those machines. But we do have to make some judgments, some compromises, and how do we do that, right? So that leads, on this I will be very, very fast. I just want to arrive at one basic concept and a couple of interesting collective utilities. And then today I will mostly talk about the problem which is the most classic for fair division, which is called I call division of mana. And this is the case where there is a bunch of resources with specific economic characteristics. They are borrowing from the standard economic model, and these resources are common property. They come to us as a gift. Inheritance, some bankruptcy when we have to divide, this time maybe not goods but bads. We have to divide cost, divorce. Common property resources that we must split among agents, and those agents have private information about their own preferences and full responsibility for that. So we are immediately excluding the idea here that thinking that my preferences could be the result of a handicap and I need compensation. No, it's not that. It's fully independent agents who have their own preferences. It's their choice. How can they then use these differences in preferences to define a fair division, which is at the same time efficient and, if possible, incentive compatible? So that has been really the main the subject of a vast literature. That's where you have a lot of contribution by economists, but also by mathematicians, more recently algorithmic and so forth. So there I will start by the sort of the canonical model for economists, the Arrow-Debreu model, and then look carefully at several subdomains and a couple of variants. I may not be able to cover everything, but so that's going to be the big part of the talk today. Okay. And tomorrow will be more on cost and surplus sharing, but let's go on, because you can spend a long time in the introduction talking about what you're going to do. Never do it. Okay. All right. So the model of welfare is, as I said, it's not going to be really a presentation in depth. It's just a review of some basic concept, which I'm sure you have encountered one way or another, but just to make sure. So we use here a simple reductionist model, which is the one borrowed from basic microeconomic analysis, which is the model of the so-called rational choice. Namely, when we think of a microeconomic agent, the standard canonical model said that this agent is endowed with a relation that we call preference relation, over the various consumptions, the various allocations that he could end up with. And this preference relation satisfied standard assumptions of being complete, being transitive, and that's about it. I mean, complete and transitive, okay, plus some standard assumptions. So here, what we do in the welfarist analysis, we do exactly that same assumption, but from the point of view of the system manager. In other words, and the consumption of the state of the world is a distribution of utilities. I mean, remember, this is the model where you know the final utilities of your various machines, if you want. So you have preferences over the utility, the profile of utility of your agents, right? And these are represented not just by a preference, but by a collective utility function, a utility function. Because, I mean, we have all kinds of theorems which tell us if and when we can represent preference by utility function. That's a well-known subject in which I will not even enter. But, okay, so, all right, so we have maximized the collective utility. And the question now is what collective utility, right? So, to make a long story short, the basic problem here is that there are two very natural options which correspond to very radically different views, and which pose, which are almost always present in instances of the application of collective utility. It's the so-called egalitarian versus utilitarian dilemma. And what I mean by that is, and this of course has very deep philosophical and political economy type foundations going back, Bentham, Rawls, and so, I mean, the list is very long. So I'm just saying that there is such a thing as a discussion, a deep discussion here. So one type of collective utility will try to equalize the final utility index as much as possible, as much as permitted by the feasibility. Another type will try to maximize the sum. Okay? But they both make sense. And the point is that a little bit of introspection shows that we typically tend to apply both of them in different circumstances. I mean, and the utilitarian viewpoint, where you aggregate the utility of your agents and you maximize the sum, well, that of course neglects a little bit the odd agent who is not much like the others. So we choose the program that the majority prefers, and the odd agent is left alone with not a very high utility. Okay, that's the price to pay. And vice versa, with the egalitarian collective utility, we take the view that improving a little bit the welfare, the utility of the person who is the least favored in society is worth any amount of sacrifice for any number of agents who have higher utility. So both are extremist. These two viewpoints are extremist, and they both, in certain circumstances, we do have utilitarian versus egalitarian reflexes. I mean, there is the classic example when people criticize the utilitarian view. I mean, there is this classic example, which I think is due to Diamond, of the person who unfortunately is in the position of piloting an airplane who is going to crash momentarily, and he has a choice between A and B, two locations, and one of them is full of people and the other has only a few people. And well, I mean, it seems that in those circumstances the immediate reflex that we have is utilitarian, namely we will crash the plane where there are fewer people, because we said that way we are sort of saving the largest number. But of course that's not egalitarian, because if you wanted to be egalitarian, you would flip a coin between A and B so that everybody has a half chance of dying at your hands. I mean, and you can apply that in many less dramatic instances. when you don't have too much information and you are talking of a large number of people, the utilitarian reflex is very deep. The egalitarian is just as well, just as much. Think of you as parents and so on and so forth. So, okay. So now, formally, egalitarian, what is the way to express egalitarian? It's actually easier to translate the utilitarian viewpoint because you just take the simple collective utility, which is the sum of the utilities, right? And by maximizing this collective utility over any subset of feasible utility profiles, you will obtain an efficient outcome, a Pareto optimal outcome, and follow your principle. For the egalitarian social welfare collective utility view, actually it's not possible to use a utility function. You have to use something a little more subtle, a social welfare ordering, and that's because you want to define your egalitarian solution in a way that's compatible with efficiency. I mean, what you need to deal with here with the egalitarian objective is the following type of situation, which is known as the equality efficiency dilemma. I mean, it's a very grand word for something which is fairly simple. Suppose your set of feasible utilities for player one, for agent one, agent two is like this. So it's a nice convex compact set. However, on the 45-degree line, there is a point which is the one where they have the highest possible equal utility, right? But that point is actually not efficient because it's possible to give more to each of them, provided we depart from strict equality, right? It's a simple phenomenon. You can easily generate such configurations. And therefore, here, the standard solution is to say, okay, well, if we will tolerate inequality if it is to the advantage of everybody, right? So therefore, instead of going in A, we should go to B. Namely, we improve, and as soon as we reach the first of these, this is the Pareto frontier. Here you have the Pareto frontier. But as soon as you reach the point on the Pareto frontier which is most egalitarian, that's where you stop, right? So to translate this, you cannot use a simple utility function. You have to use something a bit more subtle, which is the so-called leximean social welfare ordering, right? Not very complicated. It's a variant of lexicographic orderings, the lexicographic ordering where you take first the first coordinate, and if it's equal, then you go to the second. So what you do is you rearrange increasingly the individual utilities, right? So if you have a profile of utility U, you call U star the same profile but with the same set of coordinates but rearranged increasingly. And now to this profile you apply the leximean ordering. So therefore, your first order of business is to make sure that the person who has the lowest utility has it highest among all possible utility vectors. So the smallest utility should be highest. Then once this is taken care of, in that subset of allocation where that is achieved, this first maximization is achieved, then we maximize the second highest utility, and so on and so forth. Okay? So defined like this, it's a perfectly clean operation, which is the maximum exists and is unique. The maximum exists on any compact set of utility profiles, and if the set is convex, it is even unique, and so forth. So, okay. Now,
question.
Yeah.
When we do this math at the start, if we're comparing two different utility profiles, do we do the same rearrangement for both, or we just put each in descending order?
The utility profile is one for every person. So,
right.
So there is only one. And then you rearrange. You say U1 star will be minimum of the UI. U2 star will be the second lowest of these n numbers.
I see. So U can be better than B in this without being a Pareto improvement.
Exactly.
Okay.
Exactly. Yeah. For instance, here B is better than all of the other allocation, in particular all of the Pareto optimal ones. Yes?
Both concept definitions assume that you can compare one utility unit for one person to utility units of the other person, right?
Absolutely. So absolutely, that's the sense in which it is deeply cardinal. Yes.
Yeah.
The funny thing is, one important point of this lecture is to show you that this very cardinal concept have very important and, in my view, deep application in the problem of division of mana, which I will treat as entirely ordinal. So, but for this, let's go to it. Okay, all right. So this is just to show the contrast between egalitarian and utilitarian. You know, if you have two agents, you're dividing one unit of goodies. I mean, 1 unit of cake. No, but homogeneous cake. I mean, candies. And one has a utility U1, which is twice as much the utility of the other. And they are both concave in the amount of good that you give them. So marginal utility decreases. So if you are egalitarian, who are you going to give the bigger piece? To agent 2. Because he has a smaller utility, right? Agent 2, you give him the same amount of candy, he derives twice less utility than agent 1. So in order to equalize their utility, you give him a bigger piece of candy, right? But if you are utilitarian, it's exactly the opposite. Since agent 1 has a higher marginal utility, I mean, you will go higher before you equalize marginal utility. So to maximize the sum, you give the agent 1 a bigger piece of candy. I mean, so that's a simple way to illustrate the difference between the two. Okay. Now, here is, in a very short summary, the output of a large and nice amount of axiomatic work which tries to identify a subset of meaningful collective utility functions, and in my view succeeds very well. In other words, start from the top, a general collective utility function, W of U1, UN. What kind of properties should we impose on W so that it's a meaningful way to try to come up with a fair compromise between those utilities? So certainly it should be symmetric. You should treat all the variables symmetrically because that's horizontal equity. That's the first principle. You should not give a special advantage to someone vis-a-vis with respect to their names. Certainly it should be monotone in the sense that if I increase all the utilities, the collective utility should be better. That's the efficiency requirement. Now, scale invariant is already can be discussed, but it's rather plausible, right? I mean, if I scale everybody by the same factor, then my collective utility function will also be scaled by the same factor. I mean, or some proportional factor. So if you do that, there is one thing I should have, and so basically the result is like this: symmetry plus monotone plus, okay, scale invariance plus, and here I forgot, I mean, the big axiom here is separability. Separability of W. And what does it mean? Separability here means, suppose I have W of U1, U2, U3, U4, and I want to compare to W, I want to compare this to W of U1, U prime 2, U prime 3, U4. I want to know where I am better. And separability simply says, well, you don't need to know U1 and U4. All you need to know is how does U2, U3 compares to U prime 2, U prime 3. Okay? It's a very, very potent axiom which basically says, you know, if it's fair, if you know something about the local changes, you don't need to know the full information about all the entire profile to know if the local changes becomes. I know you know it's a good local change, then it should be also a good global change. So without scaling variance, these three axioms give you that the W essentially, I mean, must take UN must take an additive form. Right. And it's clear that. Right. It's clear that if my objective function has this additive form, then the separability property holds. When I say that they imply, this is not quite correct. This is almost correct, but remember the lexemean ordering. I mean, the lexemean orderings definitely satisfy separability, but like any lexicographic stuff, it cannot be really represented like that. So it's only there in a limit sense. But, okay. So you have this, and then if you add scale invariance, then you obtain this. WP of U is sum of the UI power P, where P could be negative, and therefore you put in front, you multiply by the sign of P. Why do I put this one pay such attention? Is because this is a very nice, I mean there are other, but this is the main one, a very nice family of collective utilities which allow you to, in a flexible way, to go from utilitarian to egalitarian, and by simply adjusting a parameter, which is, if you want, your own compromise between the two. For P equal 1, this is the utilitarian collectivity function, and for P equal minus infinity, remember it's minus 1 over UI to the power 100, then it pays more and more attention to the smallest of those utilities. Of course, always the utilities I'm assuming are strictly positive. I mean, I'm not, so that everything is clean. So P equal 1, you have utilitarian. P equal minus infinity, you have the lexemean social welfare ordering in a limit sense. P equals 0, very important. What do you get? Well, you get some, what you maximize is really sum of the log of UI, I mean, if you go to the limit, and that's simply maximizing the product of the UI. And that's what we call the Nash collective utility function. Nash as in Nash bargaining, not Nash as in Nash equilibrium, right? Because it's the one that in the celebrated work of Nash on axiomatic bargaining that he shows, you know, should be maximized as a result of a certain set of axioms. So this Nash collective utility function, you should think of it as a natural and very meaningful compromise between the two viewpoints. I mean, the point being that since you have a log of UI, you will never allow anybody to go to 0, right? I mean, when you maximize this thing, everybody will get something strictly positive. So vis-a-vis the benchmark 0, there is a guarantee you are not going to, do like in good old utilitarian where you could bring somebody to absolute, the old story of the sadist, the population of sadists, and one who is just a normal person, so they take a lot of utility by torturing him, You can, with utilitarian, you can make all kinds of paradoxes like that. And here, this thing, prevents you from going very, very low, and at the same time has it's a good compromise. But so keep it in mind because we will use it pretty soon. Okay, and then there are all kinds of results which show you how inside the family you can identify one or the other of these things, but that's really not my point today. Okay, one last concept, which is important for my lecture today as well as tomorrow, is the concept of Pigou-Dalton transfer and Lorentz optimality. Yes?
Is separability traditionally justified on philosophical grounds, or is it just for analytic convenience?
It's fundamentally, just like consistency and additivity in the Chaplet theory, it's fundamentally the mathematical engine. Now, okay, so now you could also say that it's it has this sort of practical practical notion that, you know, I don't need to know everything, I can just look locally. So that's that's a bit more than just saying, oh, it's because the math worked well. But it's not very deep philosophically, I agree. Right. Okay. So what's a Pigou-Dalton transfer? Suppose you start from a distribution of utility and you rearrange them increasingly. U1 star, UK star minus 1, UK star, UK plus 1 star, etc. Now, from UK star to UK plus 1 star, remember you are going up and there is a gap between them. So let's just rearrange the vector by making a little transfer from person k plus 1, from whomever has the utility u star k plus 1, to the person who has the utility u star k. So you are taking away a little bit from that person and giving to k plus to k, right? So this is an equalizing move, right? You are not changing the sum of utility, you are just reducing a little bit the inequality. Okay. It's clear that it improves any of these collective utility functions I was mentioning before, at least for p less than 1. From the utilitarian to the lexinin, when you do these kind of things, you improve. But if you were looking at sum of the ui square, if you take p equal 2, then that's exactly what you don't want to do, right? If you maximize sum of ui square, which satisfies all the actions I was mentioning before, now you are actually striving for inequality, right? If you want to maximize sum of u1 square plus u2 square, well, you give everything to one person. So in fact, what this test of Pigou-Dalton identifies is this notion of which collectivity function favors to go toward equality, and in fact also allowing utilitarian to be part of that group. Okay, and then the next notion is the notion of Lorentz domination. You said that Lorentz dominate V if the smallest of the coordinates of V is less than the smallest of the coordinate of U. The sum of the two smallest coordinate of V is less than the sum of the two smallest coordinate of U, and so on and so forth. So it's like stochastic dominance type concept. It's exactly that, in fact. So, and then you can speak about Lorentz optimality, where you are a utility profile is Lorentz optimal if it is not Lorentz dominated. So Lorentz domination is a refinement of Pareto optimality. In other words, when you are Lorentz optimal, you are in particular Pareto optimal, but you are more than that. And this is easy to see on the example, in the picture. Okay. So, if you have, I'm not taking this special case, I'm taking a case like this where the utilitarian maximum will be here, and then the egalitarian maximum will be here. So this is a case, so this is the 45-degree line. You have U1, U2. So if I am egalitarian, I will choose A because it's Pareto optimal, right? It's Pareto optimal and it's on the diagonal. That's if I am egalitarian. If I am utilitarian, I will choose B because that's where the sum is maximum. But this part of the Pareto frontier, which is bona fide Pareto optimal, is eliminated by the Lorentz domination, because when I go from here, from C to either to B or to something over here, but let's say from C to B, I am increasing both the utility of the lowest agent, the lowest utility, and the sum, right? So I am good both on the utilitarian criterion and the Lexi-mean social welfare ordering, and in fact, of everything in between when W is concave. The important result is that if W is concave, and I apply a Pigou-Dalton transfer, I am improving this function. Therefore, when I look at a Lorentz optimum, one which is dominated. When I look at a Lorentz dominated outcome, I will always improve it. I can always improve this collective utility, all of these collective utility functions for any choice of the concave utility. So, all right. So the type of result that you have are something like this. Standard little lemma, U Lorentz dominates V, if and only if you can go from V to U by a sequence of PD transfer, and here I forgot something, a sequence of PD transfer and Pareto improvements. You do some equalizing transfer, you Pareto improve, okay, and finally this is okay. So now, based on this domination, this relation, which is again stricter than, which refines the Pareto relation, I can talk about a Lorentz dominant profile, which is in some sense the dual, the type of utility profile which, if it exists, really solves all of our problems, at least from the point of view of the choice of a collective utility function. Because a Lorentz dominant profile is one which is Lorentz superior to every other profile, so stochastically dominates every other utility profile in the feasible set. Therefore, it will be a maximum, it will maximize any separately additive collective utility of the type sigma of W of Ui, irrespective of the choice of the concave function W. So in particular, it will be a Lexi-mean maximum, and it will maximize the Lexi-mean SWO, it will maximize the utility, collective utility function, the Nash utility function, and so on and so forth. So the thing is, of course, it doesn't always exist, but when it exists, it's really a complete solution to the welfarist issue, because you don't have, it eliminates completely this dilemma between being utilitarian and egalitarian. It does both at the same time. Okay? Yeah.
In the previous formulation, are you allowing for altruistic agents?
No, the agents here, remember, are absolutely just machine. It's only the only person we are talking about is the system manager, the planner, who has genuinely, these actions, the actions I was listing are actions of the system manager. He genuinely cares to reduce inequality if it is not at the expense of any utilitarian criterion and so forth, right? So that's the idea. The agents right now are really nothing. Just machines to produce utility, right? But so here is really the technical result which I wanted to arrive at, because it's an important one, both a little bit today, but especially tomorrow in the cost-sharing discussion. So again, a Lorentz optimal profile, Lorentz optimal as in Pareto optimal, simply means I am not Lorentz dominated by any other utility profile. So, for instance, in this figure, it corresponds to the interval of the Pareto frontier between B and A, and it's easy to show that for any compact set of feasible utility profile, such thing exists, just like Pareto optimum exists, but the Lorentz optimum exists. What typically does not exist is a Lorentz dominant, because here none of them is Lorentz dominant. This one maximizes U1 star, this one maximizes U1 star plus U2 star. So the only case where with two people the Lorentz dominant allocation exists would be a point which is both egalitarian and maximizes the collective utility, right? If you have a figure like this, where both the maximization of U1 plus U2 and U1 equal U2 the highest point on the 45-degree line, they coincide, then you have a Lorentz dominant solution. Okay? So that's really a lucky case. But the important fact is that there is quite a large family of problems in which those things arise naturally. And this is the thing. I mean, so this is the technical result which will be used later. So, fix, let's say, a submodular set function. I don't repeat the definition of submodular, right? Set function on the subset of M, and let the set of feasible utility profile correspond to essentially the set of core stable utility profile. But here I don't give any interpretation. I just give a mathematical definition of a set, right? So the set of feasible utility profile is the set such that U sub n is the sum of the UI equal V of n, and for any S included in S, U sub S less than V of S. And V is submodular, so this thing is non-empty. It's the core of a concave game, a concave cooperative game, if you want that interpretation. Then this set has a Lorentz dominant element. And it is obtained, in other words, this set has a most egalitarian element, which is not only most egalitarian in the sense that it makes the lowest utility as high as possible, but also the lowest the last two lowest, the sum of them as high as possible, the sum of the three, and so on and so forth. And how do you obtain it? By a simple greedy algorithm, which starts with the largest solution of this, right? I mean, so this algorithm is like this. So you want U, which is in the set in the core here, US. So you know that U sub S, sum of U over I, sum of UI I in S is less than V of S, and sum of UN equal V of N. And now what you do, you wonder who should get, how should I choose the lowest possible utilities? Well, I claim that if I look at the problem, let's look at the problem minimum over S included in N of V of S over cardinality of S, so the per capita constraint V of S over S, and let's assume that this is lambda, right? And that the argmin, the solution S star, is the one that satisfies this, that solves this problem. But now, because the thing is submodular, the nice thing, of course, is that if you have several S minimizing this function, then their union also minimizes. And that's the big thing about submodular function. So then this is the largest, here I take the largest solution, which is the union of all possible solutions if there are several. Now it's clear, so it's clear that US star is going to have to be less than V of S star, and therefore US star over S star is going to have to be less than lambda. So inside the coalition S star, I will have to go as low as lambda if I take the lowest utility, right? And in fact, if I want to be egalitarian, what I have to do, because it is exactly in S star that we will find the lowest utilities. They will be, and to make them, to maximize the leximin, to maximize the smallest, I have to give everybody in S star that particular utility lambda. I have no choice. Yes?
So this Lorentz dominant element, does it correspond to any known familiar solution concept of cooperative games?
It has been given a christening in TU cooperative game by Bhaskar Dutta and Deborah Joy, but actually late in the game. I think their paper is what, 92, 93, something like that.
But it does not coincide with, I know, per capita nucleolus. Or
No. That's what I was saying. Yeah, nucleolus Shapley value, that's in the 60s. I mean, the Shapley value is 50s, nucleolus 60s. This one introduced as in comparative gain is the delta rate in the reference of the slide. It's in the early 90s. Somehow they call it an egalitarian solution in the core. What they mean is, and I think it makes a lot of sense, if you are in a context where you have such feasibility constraints and they are submodular, and you don't want to hold agents responsible for those constraints, it's just a fact of life, and you will see that will happen in the model soon. Then this is the natural egalitarian thing in a strong stochastic dominant sense, right? So that's what you do. You give them lambda, and then you start over for the reduced problem where, for the other agents, you define V tilde of t is V of t union S star minus V of S star, which is again submodular, and you repeat. And the next step is a strictly higher utility level, and you define like this your Lorentz dominant. So that's a very useful result, because it means that if you happen to have a feasible utility set with that shape, it will be very straightforward to find a good egalitarian solution, and in a very strong sense. Okay. All right. Part 2. Whoa. I was supposed to do that fast. Okay. So now we completely leave this world of cardinal utility. On the contrary, we go to a very ordinal framework of ordinal preferences. We still speak of utility, but we really keep in mind that the only relevant information is the ordinal preferences. And these people have some resources to share, which are in the common property regime. Right? So no one is responsible for bringing those resources to be shared more than any other, totally common property. The only thing we have to take into account is the difference in tastes. And for this, we are also fully responsible, so those preferences cannot reflect needs. So in other words, it's going to be a case where if someone has expensive tastes, probably he or she is going to have to suffer from that in some other respect, right? I mean, okay, fine. Okay. So, what are the goals? What would we like to have? We would like to find a division rule which achieves efficiency. So keep in mind that since I'm going to be looking here at desirable commodities consumed privately. I mean, that's very, very important here for the whole model, that I get a bunch of resources. Those resources are good in the sense that more only increases my utility, but also I don't care about the way the other resources are consumed among other agents. So I'm not going to be altruistic or caring about the fairness of the distribution among the others. I'm looking at my own consumption, and that's what. So only the actions, the general actions, will take care of this fairness issue, but not at the individual level. I'm just looking at my consumption. Okay. So efficiency, we will need. Strategy proofness is the technical term in that literature for truthful report of preferences. If possible, that's going to be very hard to achieve, in fact. And then fairness. So fairness, that's where economists in particular have been rather creative, because I'm going to propose a bunch of tests, a bunch of properties, and claim that in a sense they are the contribution, the conceptual contribution of those people. So the first two are easy. I mean, there's nothing really new there. First, we want equal treatment of equals, same final utility for same preferences. So if two people, remember, the only way people are different is they have different preferences. So if you and I have the same preferences, we should end up with either the same allocation or two allocations which we find which we are indifferent between, right? I mean, there should not be a difference. And then you actually should make it stronger, which is this symmetry axiom. Symmetry axiom says more. It says that names do not matter. So if in the first problem where the name of the agents were 1, 2, 3 with certain corresponding preferences, if now I exchange their names, I permute everything, then of course the corresponding allocation should be permuted. I mean, I guess it's clear, right? It's the symmetry. So these are no-brainer. Now come the real meat, the real proposition, if you want. And these two, what I'm going to propose is in total 4 plus 1 tests of fairness, and the first two are what we call single profile, in the sense that these two tests apply to a single economy. You have an economy which is given by some resources and a list of preferences, one for each agent. When you look at an allocation, a division of these commodities, you can tell by just looking at the allocation and the corresponding preferences whether the test is satisfied or not. Single profile. Unanimity lower bound, which sometimes is called individual rationality. I mean, you will find it in cake division. It's called proportionality, I think. Yeah. What does it say? My utility should never be less than the utility I would enjoy if every preferences was like my own. So remember that in this, I mean, think of the standard model arrow de bleu. I mean, commodities which are divisible, and the point is that it's because you and I have different preferences that we can do better than equal sharing of the resources. Suppose it's possible to divide the resources in absolutely equal shares. That's also possible. And if our preferences are identical and convex, well, you need a little bit of convexity. If our preferences are identical and convex, and you and I have the same preferences, then it is Pareto optimal to divide the resources equally. So in that sense, there is no, and in that case, there is no issue. What makes it interesting is that you and I do not have the same preferences. So if we start each with 1 unit of each commodity, maybe you will want to exchange with me some of your commodity 2 for some of my commodity 1 and vice versa, because we have different rates of substitution between those commodities, and that's where the problem starts being interesting and difficult, right? So what this lower bound says is take the view that you can sort of interpret it as saying, well, give me 1/10 of the resources, that's the lowest benchmark, you cannot bring me lower than that, right? That's one way to interpret it. I mean, and this formulation is a bit more general. Saying you think of what, because it allows you to deal with indivisible goods and other contexts, but you can think of it in first approximation as give me 1/10 of the resources, and that level of utility is a minimum. Okay? Now the second concept, which is more demanding and somewhat related to the first, not quite, is no envy. No envy, that's something which was discovered, I mean, some people are attributed to Tobin, Foley, Cole. I mean, there are various people who contributed to the development of this idea, but it's this very nice and very compact axiom, which is that, well, when we compare after the division our various shares, what we get is at least as good from our own point of view that any other share. So in other words, I mean, one sort of incentive way to interpret no envy is to think like this. There were a bunch of resources and we prepared shares for everybody with the name tag for everybody. John is getting this, Alice is getting that. And then when they go to the table, no one is rushing. You go, you get exactly what you want. So you don't need the tags. You take away the tags, everyone goes to his favorite share, and everything is fine. Okay.
Quick question.
Yes?
If you go back to the other two tests, one third, how does the latter imply the ET, the equity?
This one's stronger than this one.
Are they really? Or
Yeah. This one is a strengthening. It's symmetric.
it's the other way around.
Symmetric. Yeah. This one says that the function is symmetric, so if two components are the same, it must be that the output is the same for these two. It's a function from a list of preferences to a list of allocations. So if it's fully symmetric and you have two inputs which are identical, it must be that the two outputs are the same.
But that you already have in the first.
No, because here you are only looking. Yeah, that's the case where they are equal. But here you are saying if I look at U1, U2, U3, and they give me Z1, Z2, Z3. When I look at the report U2, U3, U1, they should give me Z2, Z3, Z1. Even if 1, 2, 3. It's the fact that the function as a function for n variable into n other variable is fully symmetric, which is a stronger statement. Okay? But, and that's the general horizontal equity. Now, in fact, as you perhaps noticed, no NV implies equal treatment in a utility sense, right? If I have no NV and you and I have the same preferences, it must be that your share is not as good as, is not better than my share from my point of view, but from your point of view, my share is not better than your share. So therefore, we are actually indifferent, both of us, between those two shares. Okay. All right. Now, see, there are some links, but it's now two more tests, and then two more tests. This type multi-profile test. Test when we change something to the problem, so we compare what happens in two different problems, and that is also, I believe, a very important component of fairness, because in reality, I mean, it seems to me that when you think casually about fairness, and especially instances where people became aware of unfair situation, fairness is something which emerges more by its contrary, by the absence of it than the opposite, right? So what happens is a situation where some parameters change in a direction which should be clearly to the advantage of everybody, like resource monotonicity. There is more goods to distribute, and this growth, results in someone being less with a lower utility level. That's reason to protest. See, so it's this test when the mana increases, the utility of every agent should also increase weekly, at least weekly. It should not be the case that when you have more to eat together, somebody has to tighten his belt more. Right? It's very, very unnatural, right? And similarly for population monotonicity. Remember, we are dividing commodities which are desirable. So we were 10 to share these particular resources. One of us left. Now, it's good news. Should be good news because we have more to share. So these two things are both convincing as tests of equity. They also have an incentive interpretation. You could say that suppose a mechanism violates resource monotonicity. Then, if I can discover some new resources to be added to the one to be shared, I will sometimes not want to do that, because by adding something to the pot, bringing something more to the table to be shared, this might turn to my disadvantage. So I may not want to do that. So, and similarly for population monotonicity, if I can prove that some of us do not have any rights to be here at this table, should I really say it? I mean, all the monotonicity axioms, I mean, they typically have this dual interpretation. One as fairness, the other as some kind of incentives. If you put the not incentive to reveal preferences, but some sort of incentive. Okay. All right. But consistency, it's something related to separability. It doesn't really play too much of a role in that theory. but it's really the analog of separability. It says when an agent leaves and takes away the share assigned to him, the rule restricted this time to a smaller population should still assign the same shares to the remaining agents. So it's a way of saying that if the division among 10 people was fair, and if you look at the subset of the division, how these 4 particular agents are, what shares they are assigned, then it should remain fair. So it's similar to separability. Oh, okay. So now, just one remark to say that both resource monotonicity, population monotonicity, consistency, even strategy proofness are not by themselves, I mean, they are compatible with silly rules like fixed priority rules, right? And when you take the rule which is simply fix a priority ordering of all your agents once and for all, and whenever there is a problem, resource to divide, just give everything to the person with the highest priority. So that sort of rule, which is of course grossly unfair in the sense of equal treatment, anonymity, also the unanimity lower bound, or no envy. I mean, it's grossly unfair from the point of view of those tests, single profile tests, but it's fine as far as resource monotonicity, population monotonicity, strategy proofness. You know, who would want to lie in such a situation, his preferences, and so on and so forth. So this is just to say that you really need to have any solution which is of value, you need to have at least one of those equal treatment, anonymity, unanimity, lower bound, no envy. You need something which guarantees some minimal level of fairness. Okay, so now let me start now with the results. And general Arrow-Debreu context first. Okay, so that's in some almost the broadest context in which you can cast fair division problems in of those family. Not quite, but it's by almost standard microeconomic assumptions. You have a set of agents, a set of goods or commodities, capital A, and a vector omega. It's a certain amount of each commodity, and each commodity infinitely divisible. And now you have preferences by the agent, which are monotone, more of each good is good, convex, the upper contour, if I take any allocation and I look at the upper contour, namely the set of allocations which are weakly preferred, that's a convex set. Continuous, that says that the upper contour of any allocation is a closed set. And these preferences are representable by a continuous utility function. And now what we call a feasible allocation is a vector Zi of non-negative shares of every good such that the sum is omega. Okay? And the efficiency is the fact that the upper contour sets of the preference relation at the share Zi have a common hyperplane supporting them. That's the Pareto optimality. I mean, I go a little fast, but it's just just to say that because of this convexity monotonicity assumption, we have a good grasp of what is efficient. And we have a couple of pretty bad news. Which were the first to appear in the literature in some sense, right? I mean, the literature produced initially these negative results on things that cannot be done, and that's worrisome in some sense. So look at the first one, which has nothing to do with incentives, which is about fairness versus efficiency. It says that if you want a method which is efficient, Pareto optimal, satisfies the unanimity lower bound, and that you get at least 1/n. In this context, it's really, I get at least 1/n of the resources, and is resource monotonic, so when there is more to share, everybody should be happier weakly. Well, that's not possible in this general dimension. Similarly, if you replace the unanimity lower bound by no envy, you want a method where there is never envy, and also it's resource monotonic, well, that's not possible. Of course, if you take off efficiency, just divide the goods equally and that's it, and ignore preferences. But if you want efficiency, that's not going to work. The proof of that is very simple, in fact. It's a very simple fact which has to do with strong complementarities in the preferences. Okay? Namely the so-called Leontief preferences. Remember Leontief preferences, I don't think. Okay, what's Leontief preferences? So now my pictures now is in the space of allocations. I'm no longer in the space of utilities, of course. Here I'm talking of X and Y, let's say, good X and good Y. And a Leontief preference will be one such that there is a ray, a straight line in the positive orthant, and your indifference contour will be like this, right? Positive orthant attached to one point of the ray. So if you want to define it properly, you say U of Z is the minimum of Z X over beta 1 and Y over beta 2. If Z is the vector XY, what you are looking at, basically you want X and Y in fixed proportions, and you are looking at the minimum of those two. In other words, if you are over here, you are wasting some of the commodity because you could take away all of these commodity of good X and still be on the same indifference level. So it's the maximal complementarity. So you can use those to create the impossibility as follows. Okay. So imagine that you have two agents with both Leontief preferences, but on different lines. And think of those two. So agent 1 is here, agent 2 is here, and they have, the rays are different, and imagine they are symmetric vis-a-vis the diagonal here, which is the 45-degree line. And initially the resources are over here. So here, what I'm going to write is omega over 2. And so, for instance, it's this is the first agent. The first agent would have mean of X and Y over 2, and the second agent would have mean of X over 2 and Y, okay? And the initial resource is on the diagonal. So by symmetry, which is not the axioms of before, but let's also assume, and that's not difficult to adjust the proof, that the division is perfect. I mean, so there is a perfect way if I have 3 units of each to divide, and this kind of preferences, then the nicely symmetric way to divide is to say, okay, Z1 of the first agent is going to be 1, 2, and Z2 of the second agent is going to be 2, 1. Okay? The axioms do not require that, but you can do the argument here, and that's then adjust. It's easy. Okay, so initially we are there, and we are happy because we have exactly the right proportions to take advantage of our complementarity as much as possible. And now the omega over 2 increases till the level here, which is if this was 3/2, 3/2, now it would be 3/2 over here and 3 here. Okay. So because of resource monotonicity, it must be that agent 2 is still at least at the same utility level or more. So agent 2 is going to get at least the commodity, the allocation Z2. That's the least you can give him to guarantee that he gets at least this utility level. So therefore, agent 1, since this is now the new omega prime over 2, therefore agent 1, since we must give at least Z2 to agent 2, must get at most the symmetric of Z2 vis-a-vis omega prime over 2, which is somewhere over here. At most, this, call it Z tilde, that's the maximal, the largest feasible vector you can give him if you want to give at least Z2 to agent 2. Right? But you see that this, by the construction with the symmetric of Z2 vis-a-vis this is precisely on the initial indifference contour of agent 1. So in fact, agent 1 is not progressing. Right? So in this increase of commodities, you cannot increase basically the payoff of agent 2 or the payoff of agent 1. Right? Yes?
But I thought the requirement was only weekly, right?
Yes, yes.
So that's fine. Neither of them have got any worse off.
Right. No, that's fine. And then, okay, so then you go here. Right. Then you go here and you say that when you go to this, this increase, it's the same thing. I mean, they also remain on this utility level. And then what's the other one? Let's see. And then you have a contradiction of efficiency by what?
Have you used the unity lower bound?
Exactly. Thank you. Yeah. I did not even need to do this one. Yes. I went over. That's the usual thing. Okay, so I'm not doing just one move. Yes. I'm just doing one move from omega over 2 to omega prime over 2. Thank you. So I said that one should remain at that level, but his unanimity level has increased. That's it. Yeah. That's so it's no more than that. His utility, his guaranteed utility level has increased because now this is half of the resources, so it should be at least here. So that violates resource monotonicity for the other. Okay, so that's it. I mean, this is something we will not be able to achieve if we allow for any level of complementarity. Okay. Of course, the natural question to which I will come soon is, what if we restrict complementarity? Okay. Now, second impossibility, much more famous, by the way, than those ones, and much more, starting in the literature much earlier, because this starts with the work of Hurwitz, Leo Hurwitz in the late 60s, early 70s. How about strategy proofness, incentive compatibility in the sense of truthful revelation of own preferences? Well, efficiency plus guaranteeing the unanimity lower bound, or here guaranteeing the 1/n, the utility level of 1/n of the resource, plus strategy proofness, that's not possible. You can even have stronger than that. I mean, not stronger, but actually more difficult to prove. Efficiency plus equal treatment plus strategy proofness, not possible. Okay? The first result is essentially the one that Hurwitz was sort of proving intuitively in the 70s. It took almost 20 years for Ling Zhao to come up with a correct proof of that. And this one, another 10 years. I mean, those are hard results. Hard results. And also tough. Tough because it means that, with strategy proofness, well, we are not going to go very far. I mean, if you look at the second, I mean, you're not going to go very far if you want strategy proofness and efficiency. And as far as the trade-offs between strategy proofness and efficiency, there is some work, but nothing which is in the style of quantifying the price of anarchy and so forth, because we are in a world of purely ordinal preferences. I mean, of course, you could cast those questions in a context where utilities are cardinally measured, maybe quasi-linear utility and so forth, but this has not been done. Perhaps. Okay. All right. Now I come to. Okay. So now, what is the next step? The next step is to propose two rules, which I think of as being the positive contribution of economic analysis to this third division problem, namely two solutions, two ways to achieve the division, which will work in full generality in this Herve Moulin domain. And these are the CEEI, competitive equilibrium from equal income, and then immediately after the egalitarian equivalent solution. So what's competitive equilibrium with equal income? It's exactly the application of the competitive equilibrium notion, the variation equilibrium and so forth, but with a twist, with a fairness twist, which is that we impose equal incomes, right? You could think of it in the Herve Moulin as saying we give everybody an endowment which is 1/n of omega. That would amount to the same thing, but it's actually more convenient, I think, to think of it as saying that they have the same income, and we find the price vector P and some feasible allocation Zi, such that basically when I say P omega equal n, it means that the budget of every agent will be 1. The total price, the total monetary value of the commodities will be n, so each one will have a budget of 1, and the Zi, what agent I consumes, maximizes his own preferences over the budget set, which is he can buy anything which costs at most 1 at this price. Okay, so it's a really application of the standard competitive allocation, competitive equilibrium notion. It requires the convexity of preferences to guarantee existence. If you didn't have convex preferences, you could not be sure that such a thing exists. And also uniqueness is not at all guaranteed in general. And you can have multiple equilibria in a serious way, in the sense that they give you different utilities to the different at the different equilibrium allocations. So it's not like a trivial non-uniqueness, except in some special context. In particular, homogeneous preferences, to which we come soon. And you can see also that by construction, it's going to meet the tests of unanimity lower bound and no envy. I mean, unanimity lower bound is obvious. It's because by the construction of this price, I always make it feasible to buy omega over n. Since the price of omega is n and everyone has a budget of 1, you can always buy omega over n. So omega over n is always in your budget set. So since you have an allocation which is the best in your budget set, it's at least as good as omega over n. So you guarantee to be at least at that level. Now, moreover, you guarantee no envy because everybody is choosing in the same budget set. So in that same budget, the same common budget set, I chose my favorite, you chose your favorite. So therefore, I cannot be worse off than with your own share, because I could afford to buy your own share according to the competitive price. So no envy is really hardwired. Notice, by the way, that if you have a model in which agents become negligible, there is a continuum of agents. There are some very classic results which shows that if also you need some connectedness assumption on the list of preferences, but basically CEEI can be characterized in that world by efficiency plus no envy. I mean, if agents become very, very small vis-à-vis the total economy. Okay, fine. But on the other hand, there is no way, I mean, they are not going to satisfy resource monotonicity or population monotonicity. I mean, resource monotonicity, we just know from the impossibility result before. Population monotonicity, that requires a little proof. Okay. So, okay. Now, second concept, egalitarian equivalence. Much later concept, which in some sense is much more primitive concept, much less elegant and sophisticated than this idea of price and balance of the price and the demand of all the agents sum up to exactly omega. It's a much more simple idea, which essentially is using the vector of resources as a benchmark to measure, to give a cardinalization of all the preferences into a utility. So when you look at this expression here, Zi is indifferent for agent I to lambda omega. It means that the allocation I will give to agent I will be equivalent to a certain fraction of the total resources, and the trick is that this fraction lambda should be the same for everybody. So everybody can say, I mean, the argument of fairness here is to say what you get amounts to a 60% fraction of the total. Let's say you have two people, so we should be all entitled to 50% of the resources, but because I take advantage of differences in preferences, I make sure that in the end everyone is each of us is consuming something which is equivalent to consuming 60% of the total resources. Okay? That makes good sense. Notice that existence here does not even require convexity of preferences. Well, there is also another notion, I mean, a bit more general, where you take an arbitrary vector as your benchmark, but let me skip that one. And, well, the good thing about the egalitarian equivalent rule is that it guarantees the unanimity lower bound, because it's always feasible to give everybody 1/10 of the resource, right? So you can do typically more. But of course, it will fail the resource monotonicity property, because we remember that we have this incompatibility. Okay. And the other one, I put it there, the one where you take an arbitrary vector of numeraire and you take this one as benchmark, irrespective of what is the omega. The advantage is this one satisfies both resource monotonicity and population monotonicity, but then of course it violates the unanimity lower bound, and etc. Okay, all right. So, okay, so now I have, very quickly I want to go to a short example to show the difference between those two concepts, and then I want to go over some special domain of preferences where this fairly negative picture of the two impossibility result, in fact, becomes much more optimistic. I mean, gives more hope for more results. Okay, so right here it would be an example where I'm not going to go over the computations because they are in the slides and the slides are available. But basically, you have agents with linear preferences. Type X, there are two goods. Type X have utility 2x plus y, so they prefer good x to good y. And type Y have utility x plus 2y, so they prefer symmetrically good y over good x. And the endowment is symmetric, but in each good. But what is not symmetric is the number of people of type X versus the number of people of type Y. Okay? So you may have, if you have a fully symmetric case where there is exactly the same number of people of type X and people of type Y, then both solutions will actually recommend that they share. What will they do? I mean, imagine here you have exactly the same endowment in each good and the same number of agents of type X and the same number of agents of type Y. Then the obvious sort of symmetric thing is to say, look, I mean, type X, they love good X. Let's give them all the good X, none of the good Y. And type Y, they love good Y, we give them all the good Y. Right? I mean, efficiency here would simply say, if you give any amount of Y to a type X, you should not give any amount of X to a type Y. So efficiency is compatible with giving everything to the good X, but then nothing to the good Y. But if you want fairness here, and both of these concepts, CEEI and egalitarian equivalence, they would recommend exactly that. I mean, to give them, to give all the good X to the type X, all the good Y to the type Y, and okay, that would be the case of equal amount. But now, if the numbers are different, the two solutions behave completely in opposite directions, because the CEEI will actually reward people with rare preferences. So if I go from a situation which is 50-50 to a situation 60-40, and I look at the utility of the, let's say I had 50-50 type X, type Y, and I go to 60-40 type X, type Y. In the CEEI, those 40% of type Y will find themselves better off because they are more rare, and the price, their preference is more rare. The commodity in higher demand is the commodity X, so people who are type Y will be able to get more Y, and in fact they will be able to get all the Y within a certain range of the density of the frequency of the two types. They get all the type Y, okay. Whereas the egalitarian equivalent will do exactly an opposite thing. It will say, okay, well, I will leave everybody to the same virtual fraction of the total resources, and as a result, when I go from 50-50 to 60-40, all of the initial 50% of type X and the initial 40% of type Y, those who have not changed type, they will all go down. They will all suffer jointly. I mean, the most favorable situation for this economy is when there is an exactly the same number, because the mutual benefits are highest. But under the egalitarian equivalent, when this is reduced, then they all suffer. So they go in very different direction, and you can think about it. I mean, you know, both make sense. It's just very difficult to come with a systematic thing. So here are the computations. Okay, see what the thing decreases and so forth. All right. Okay. There is also a fact which I've noticed that fact a few times, but I've never seen any formal work on that, which is that under CEI, the misreport, the temptation to misreport, the benefit from misreporting is much less than under the egalitarian equivalent solution. I mean, this is something that could justify some research, but I'm not exactly sure how to approach it, because, you know, if you want to be a little general and so forth. But okay. All right. So okay. So now I come to the last part. I was hoping to be there a bit earlier, but because this is the part where I think we will finally get to some connections to the more algorithmic literature that Ariel was mentioning, and in which he was also acting. And it is the question here is that of subdomains. I mean, one way to put the thing, 20. Yes. Oh yeah. Then okay. No, I was okay. Thank you. So, okay, so I will spend some time tomorrow to tell you the goodies that are here. Now, it's a good point to stop anyway. I'm sorry, I really was thinking of before, but okay, so we'll stop here, and tomorrow we'll discover a much nicer picture in the world of subdomains. Okay, thank you.